Hi, this tutorial is on optical isomerism. So optical isomerism is just a version of stereoisomerism. And stereoisomers you have seen when you looked at alkenes. You've had a little look at how to determine whether an isomer is the Z form or the E form if there's a carbon-carbon double bond in it. And if you remember, you should have had a definition for stereoisomerism. So stereoisomers have the same structural formula but a different arrangement of atoms in space. And just remember, that bit, different arrangement of atoms in space, is really, really important that you just learn that as a phrase. It's so common that people try and write the definition from their own ideas and end up making it sound like structural isomerism. So if you learn that phrase, then you won't lose your marks in your exam. So just as a recap, looking at these two compounds at the bottom, you have got a carbon-carbon double bond. And if you look at the left carbon, the substituents, you've got a green and a yellow. And on this one, you've got a green and a yellow. On the other carbon atom, you've got green and yellow. And again, you've got green and yellow. So these two compounds would have exactly the same structural formula. So I've just given these coloured atoms an identity. So I've put the green ones to represent chlorine atoms and the yellow ones to represent hydrogen atoms. So you can see that if you were to give these atoms a structural formula, you've got CHCl, CHCl. And on this one, CHCl, CHCl. So they have the same structural formula, but they do have a different arrangement of atoms in space. And if you remember, that is due to the fact that there is limited rotation around that double bond. So you cannot rotate this portion of the molecule around to make it look like this portion of the molecule. That means that these two are different compounds. So optical isomerism fits this definition as well. Optical isomers have the same structural formula but a different arrangement of atoms in space, only this time it is not due to a double bond and the lack of rotation. So we'll have a look at optical isomers next. So where EZ isomers or geometric isomers come about because of lack of rotation around a double bond, optical isomers come about due to the presence of a carbon atom, which we describe as asymmetric or chiral. So an asymmetric carbon atom or a chiral carbon atom is a carbon atom that has 4 different groups attached to it. So if you just look at this bottom compound, you can see you've got an orange atom, a green atom and 2 white atoms. So this doesn't fit our definition of a chiral carbon. It doesn't have 4 different groups because 2 of them are hydrogen atoms. And you can see that you wouldn't describe this as asymmetric. This compound is symmetrical because it does have a line of symmetry. If you imagine looking from that direction down the molecule so that your green atom and your orange atom line up, you would see that to the left you have a hydrogen, to the right you have a hydrogen, and they would be mirror images of each other, so there's a line of symmetry, and your green and your orange would be in line, so you'd have green with orange behind it on the left hand side and green with orange behind it on the right hand side. So there is a line of symmetry through the molecule if you look at it from that direction. So when you're looking for optical isomers, they will always have a carbon atom that has 4 different groups attached, and that is the basis of optical isomerism. So here we've got 2 molecules which have a chiral carbon in the middle. So this one has green, purple, orange and white, and this one has green, purple, orange and white. You might be tempted to look at these 2 compounds and think that they are actually the same molecule, but they're not. These are non-superimposable mirror images, and this is your key to being able to draw optical isomers so the 2 optical isomers of a compound. If you can draw a mirror plane, and you can draw them either side as mirror images, and as long as they've got 4 different groups attached, you will be able to draw optical isomers. So this idea of a chiral carbon, chirality actually means handedness. So we can refer to these as left-handed and right-handed versions of the same molecule. And you can see that they are non-superimposable because although they do look like mirror images, you can't place one on top of the other and get them to match up and look the same. So here are my 2 versions of the same molecule with a mirror plane down the middle. You can see that they are mirror images because at the front you've got your 2 orange atoms, which we'll call bromine. At the back we've got 2 hydrogen atoms. The sides we've got 2 iodine atoms, which are the purple ones, and pointing upwards we've got 2 chlorine atoms. So they are mirror images, and I can rotate them and they're still mirror images. I can can rotate them again, and they're still mirror images. I can turn these round, and I can get them to be mirror images in any direction. However, I cannot take one and place them on top of each other. So if I line up my hydrogens and my chlorines, you will see that the iodines and the bromines don't match up. So if I rotate it around to get the bromines to match up, you can see that the bromines and the hydrogens match up, but now the iodines and the chlorines don't. So you cannot get these. So line up my green ones, line up my white ones. You still can't get everything to line up. They are non-superimposable. Now, as I said, chirality means handedness, so you can compare this with your hands. So if you look at your hands, they're probably close to being mirror images of each other, but they are not identical to each other. So you can see that my thumb to my index finger has the same sort of distance on both hands. And next to my index finger is my middle finger, and next to that is my ring finger, and next to that is my little finger. So everything is connected to the same parts in the same way, with a palm in the middle. However, although they're mirror images, I cannot superimpose them to get everything to match up, in the same way that I couldn't superimpose those two compounds to get everything to match up. It just doesn't work. Okay, I could turn one over and place it, but then this one is palm up, and this one's palm up and this one's palm down. So they still don't superimpose, not properly. So these hands are exactly like these molecules in that they are non-superimposable mirror images of each other. Okay, so one of the problems with optical isomers and being able to get these ideas down on paper in an exam is that it is very dependent on being able to see compounds in 3 dimensions. If I draw these compounds that I've got up here in 2 dimensions, as we normally would, you'll see why this becomes a problem. So this is what they would look like drawn out in 2 dimensions. The issue is, although they are mirror images of each other, according to this sort of setup, you could take this molecule, you could flip it across, and it would sit directly on top of that molecule. So they would be superimposable, and they're not. So the 3 dimensions is really, really important to be able to understand how these molecules are different. So this means that rather than drawing things in 2 dimensions with 90-degree bond angles, you're going to have to draw in 3 dimensions. So the way that we do that is we take our central carbon atom, and anything that is in the plane of the paper, so flat against the paper, which in this photograph looks like this chlorine is flat and this iodine is flat, whereas this sticks forward and this sticks backwards. We'll class these 2 as the flat ones, and these 2 as the flat ones. Chlorine is flat against the paper, that bond is in the plane of the paper, and that iodine is also in the plane of the paper. Now, anything that points forwards out of the paper, you need to draw that bond showing that is coming towards you, and we do that using a wedged bond like that. So we'll put bromine on there, and anything pointing away should be a dashed bond like that. So that is how we would draw it in 3 dimensions. It shows that one thing's pointing forwards, one thing's pointing backwards, and these 2 parts are in the plane of the paper. So it is between these 2 parts, if you've got a tetrahedron, or slightly distorted in this case, but if you've got a tetrahedron, that bond angle is your 109.5 degree bond angle. Okay, so nice and simple. To draw your mirror image, to draw your other isomer, draw in your mirror plane, and you're absolutely fine to do that in an exam. There's your carbon, there's your chlorine that's in line with the paper, there is your iodine, in this case bromine is pointing forwards, and hydrogen is pointing backwards. And you can see that the way I've drawn them, they are mirror images of each other, but they're non-superimposable. Now this is something you could be asked to do, and probably will be asked to do in an exam situation, is you might be given 2 structural formulae and be asked to draw the 2 optical isomers that can exist with that structural formula. So draw one using this system with the wedged bond and the dashed bond, draw a mirror plane, and then draw its mirror image, and that's fine. Now the 2 different optical isomers that can exist for a structural formula, so this one and this one, these are known as enantiomers. So I've just called these 2 enantiomer 1 and enantiomer 2. Right, so they're called optical isomers, and that is because they have a strange property, which is they are able to rotate plane polarized light. So here we've got here we've got a little diagram showing you what I mean by that. It's a little bit tricky to show in a diagram, so I have put a card up in the corner that where you can watch a video, which shows it a little bit more clearly. But basically, light is a form of electromagnetic wave. So light leaves a source and it oscillates in all directions. So some of it will go up and down, some of it will go side to side, there'll be some on diagonals, but it will oscillate in all directions at the same time, and that's what this part of the diagram shows. Normal light oscillating in every direction. Now, plane polarised light is where you're able to take away the oscillations in all directions bar one. So we can take the light that's oscillating in all directions and we can put it through a polariser, and that polariser can block out all other oscillations of light apart from the one that's just going directly up and down. So this light now is plane polarised. This was unpolarised, this is plane polarised light. So once you've got plane polarised light, if you were to shine it at a sample of a compound that is optically active, so made of two opposite enantiomers, if you shine it through, if you've just got one of the enantiomers in here, one version of the molecule, the light will rotate so that the plane that it is oscillating in is rotated by a certain angle. And if you have a sample containing the opposite isomer, the other isomer, it will rotate light in the opposite direction, so that it oscillates by the same angle but the opposite way. So this is really important. It's such an important feature that they have. Now, if you were to fill this sample tube not with a single enantiomer, but with a 50-50 mixture of both the left-handed molecule and the right-handed molecule, the effect of the left-handed molecule would cancel out the effect of the right-handed molecule, and actually what you would get is the light that's oscillating vertically would continue to oscillate vertically. So you wouldn't get any effect on plane polarised light if you've got a 50-50 mixture of the two enantiomers. So a racemic mixture, or a racemate, is a 50-50 mixture of the two enantiomers. So a racemate or a racemic mixture will not affect plane polarised light because one enantiomer's effect will cancel out the other enantiomer's effect, and your plane polarised light will continue to oscillate in the same direction that it was before. So this is an important definition. Racemate, also known as a racemic mixture, means 50-50 mixture of the two enantiomers. And if you're to synthesise these sort of things in a laboratory, the chances are you're probably going to get a racemate or a racemic mixture, which you would then have to separate out into the two enantiomers if you wanted to get a compound that would rotate plane polarised light. So in an exam, you would need to say that optical isomers, the two enantiomers, are able to rotate plane polarised light in opposite directions, and you'd also need to know that if you've got a 50-50 mixture of the two, there would be no effect. Now, you don't really need to know much about how this is measured, but if you wanted to know how do you measure the angle by which the plane polarised light is rotated, what you would do is where you've got a polariser here, which blocks out anything apart from a vertical oscillation, you could take another one of those polarisers and place it at the end. Now, if it was pointing upwards like this, you'd get no light travelling through because it would block out the plane that that light is currently oscillating in. But what you could do with your polariser is you could slowly rotate it round so that the slit, essentially, that's in it is rotated, and eventually you'll rotate it to a certain angle and that light will be able to travel through. So you can use how far you've rotated your polariser before the light actually gets through to determine the angle that the light has been rotated by your optical isomers. So just some definitions that you need to be aware of. Chiral carbon is a carbon atom that is attached to 4 different groups in each direction, and it's sometimes known as an asymmetric carbon atom, or even sometimes a stereocenter. Okay, chirality is a property of compounds that have a carbon atom attached to 4 different groups, and also some other compounds that might not have a chiral carbon can also be chiral. Basically means handedness. So left-handed and right-handed versions of the same things. You also get chirality in things like screws that you use in woodwork. So screws can spiral one way or they can spiral the other way. That's a version of chirality as well. So it just means handedness. Enantiomers is just the word that we use for optical isomers. So you would have two enantiomers for one compound or for one structural formula, and they're not the same molecule because they're non-superimposable mirror images. They are actually different. Okay, optically active just means a compound that is able to rotate plane polarized light. And a racemate or a racemic mixture is a 50-50 mixture of enantiomers. And just remember that a racemate has no effect on plane polarized light. And finally, plane polarized light just means light waves that are now oscillating in one plane only rather than in every direction. Okay, so something that you might be asked to do in an exam would be to spot chiral carbons. So I've deliberately chosen quite a complicated molecule here so that you realise how easy it actually is to spot chiral carbons. Now, if you remember, the important thing about chiral carbons is if they're not drawn in 3D, you can't tell that they exist. So you can't tell that there's optical isomers. So straight away, in this molecule, this is cholesterol, I would look for anything that's wedged or dashed. So here, there's a wedged bond, which suggests that the hydrogen must be on the dashed bond. So I would suggest that that one is an is a chiral carbon. Also, we've got another wedged bond there. That must be chiral. We've got a hydrogen on a dashed bond, so hydrogen pointing away. So that's chiral. We've got a wedged one. So that one's chiral. Another dashed one, that one, and a wedged one, that's that one. We've got a dashed one here, and we've got a wedged one there. Okay, so all together in that compound, 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 chiral carbons in a cholesterol molecule, and that is a really, really easy way to spot them straight away. Now, they might not give you something this complicated, or they might give you something much simpler, but they might not make it very easy to spot that you've got wedged and dashes. They could even draw wedges and dashes where you've got the same thing coming off one of the carbon atoms, so it's not actually chiral at all. It doesn't have 4 separate groups attached. So I'd be careful because there's no reason why they can't do that. But I know with skeletal formula it's quite easy to spot when you've got a wedged or a dashed bond. There must be something there that is chiral. So usually in your exam they'll ask you to denote any chiral carbons using a little asterisk, so you can get used to putting little stars in the right places, and I'll get you to do that in class as well and have a little go at practicing spotting chiral carbons. Okay, now we're going to talk about something that's a little bit beyond what you need to know for A-level. So if you don't want to pay any attention to the rest of this, that's fine. But I know some people are looking into things like thalidomide, which is the whole horror of thalidomide and what that did to pregnant women and to their unborn babies. That is all based on scientists not realising this property of optical isomers. So if you're looking into things like thalidomide and the story behind that and how scientists discovered the 2 different enantiomers doing 2 different things, one curing the morning sickness and one causing these horrible deformities in unborn babies, you will come across in your research enantiomer notation. So if you think about the other type of stereoisomers, so if I just draw out a couple of geometric isomers with different alkenes with the same structural formula, like this, you know that you would have to name these 2 differently so that you can tell the difference between them just by looking at their name. So where you've got things that go across the double bond, they're on opposite sides, you should know that this is the E isomer of whatever it is that we're looking at, and where you've got things that are on the same side, you should know that that is the Z isomer of whatever it is, and then the name is the same for each of them after that notation. Now the same thing happens with optical isomers. They will have the same name, but they will need some notation so that you know which one you're looking at. And I just want to warn you that if you look into this, it might get a little bit involved and a little bit confusing, so I'm going to very briefly just point out the different notation that you might come across. Okay, first of all, you might see a name of an enantiomer with a plus at the start or with a minus at the start. So you can get positive versions of a compound and negative versions. And all that means is that if you were to pass plane polarised light through this compound, the positive enantiomer, the plus enantiomer, would rotate the plane polarised light clockwise, and the minus enantiomer would rotate it anti-clockwise. So you don't need to be able to do this, you don't need to be able to assign this notation to anything, but just in case you come across it, just out of interest, that's why I'm going through it. So the positive and the negative is all to do with the direction that these enantiomers rotate plane polarised light. Okay, you might also come across a name with a D in front of it, this is lowercase, or an L in front of it, again, lowercase. The D stands for dextrorotatory, which means you rotate to the right, and the L stands for levorotatory, meaning you rotate to the left. So positive enantiomers can also be known as D enantiomers, negative enantiomers can also be known as L enantiomers. So they are the same naming system based on the same principles, but positive and negative, or D and L. You can use either or. Now, confusingly, this is why if you look into it, you will throw yourself a little bit, you can also get, in fact, I'll move this over. So D and L, and these are small caps, so they're capital letters but smaller than the rest of the text. And this naming system with the small caps is completely different from that naming system with the lowercase, even though they use the same letters. So where these ones refer to the rotation of light, left or right, these ones are a bit more of an arbitrary system that somebody came up with when they were dealing with sugars, and they just decided that one of them would be D and one of them would be L, and it was to do with the position of an OH group on the compound, and it's not got as clear rules as the other naming systems, so that one's quite a confusing one if you come across it, because it doesn't really use the rules that you've seen here. So that means that you could get a D enantiomer that, using this naming system, is actually the L enantiomer. You get the L enantiomer here that's actually the D enantiomer in this system, or you could get the D enantiomer there is the same as the D enantiomer there. It's not as clear cut, the rules. So there's another naming system. We've got R and S enantiomers, so you might come across these as well if you're reading about it. And again, don't forget, you don't really need to know this yet. It's not that important at the moment. You certainly wouldn't be expected to do this in your exam. But R is for rectus, meaning to the right, and S is for sinister, meaning to the left, and it is not to do with rotating plane polarised light. It's actually to do with the configuration of the molecule around the chiral carbon. And it uses Carn-Ingold-Prelog CIP priority rules again, like you saw with the alkenes, deciding which group's your priority, and therefore is it E or is it Z. It uses the same sort of system. So if you look at the chiral carbon and the groups that are attached to it, so this is our stereocenter, our chiral carbon, you have 4 different groups attached, and I've drawn these all in black. They're all different groups. This makes it chiral. You would apply the Carn-Ingold-Prelog priority rules to these 4 groups and give them a priority number. Then if you orientate the molecule so that priority number 4 is pointing away from you, and list the priorities for the other 3 as well, then going from 1 to 2 to 3, you look at which direction you would go around the molecule. So in this case, 1 to 2 to 3 goes that way. So it goes off to the right. So this is the rectus enantiomer. And this other one, if we look at the priorities for this one, and that's priority 1, that's priority 2, and that's priority 3. In this case, we go round to the left to go from 1 to 2 to 3. So that one would be the S enantiomer. So R for rectus, meaning right, S for sinister, meaning left. So the plus and minus, the small lowercase d and lowercase l, these are to do with which direction the plane polarised light is rotated by one of the enantiomers. The R and S, and the D and L as well, with the small caps, are to do with the configuration, the groups that are around the chiral carbon, but the R and S is a little bit more of a got a little bit more of a system to it. So it's Carn-Ingold-Prelog priority rules. Make sure the lowest priority is pointing away, and then find out which direction you would go around the molecule to go from 1 to 2 to 3. If you go to the right, it's rectus, which is R, and if you go to the left, it's sinister, which is S. And this system, you have to name each chiral carbon in your compound with an R or an S. So if you think back to something like cholesterol, which has got 8 chiral carbons, you'd have 8 of these letters throughout the name to identify at each chiral carbon which way around the conformation is, whether it's in the R version or the S version. Okay, so that's all for optical isomerism. If you can make sure that you have got your lecture notes from this tutorial and you bring them to lesson, and please go onto the blog and complete your post-tutorial quiz, that would be great. Thank you.